9.6, the ratio and root test. Alright, let's look at the ratio test first. The first theorem is theorem 9.17 is ratio test. It said that let sigma a sub n be a series with non-zero terms. Alright, the series sigma a sub n converges absolutely when so you basically you have to find another term of a sub n called is a sub n plus 1, put in ratio a sub n plus 1 over a sub n under absolute value as limit n go to infinity. So it has to be less than 0. If it's greater than 0, it diverges. If it's equal, if it's greater than 1, not 0, sorry. If it's greater than 1 or equal to infinity, is diverges. And if it's equal to 1, is inconclusive. Let's look at our example. I have a sigma n from 1 to infinity, 1 over n factorial. So my a sub n will be this term here, which is 1 over n factorial. I'm going to put them in ratio with a sub n plus 1. So wherever you see n, you're going to put plus 1. Right? So you're going to have 1. Instead of n, I'm going to have n plus 1 factorial. A sub n is just 1 over n factorial. Because we have division here, I changed to multiplication, so I reciprocal the second term. Then I have n factorial over 1. Now n plus 1 factorial, I'm going to rewrite it as n plus 1 times n factorial. That's the same thing. The reason I do that because I have n factorial here, I want to cancel with the n factorial here. So I cancel the n factorial and the n factorial. I left with 1 over n plus 1. When you take a limit as n go to infinity, you have 0. 0 is less than 1, so it converges by the ratio theorem, ratio test right here, the first condition. Now let's look at our example, example 2. I have sigma n equal to 1 to infinity, n factorial, n to the n divided by n factorial. So this is my a sub n. A sub n plus 1 will be, wherever you see n, you're going to replace by n plus 1. So you're going to have n plus 1. Instead of raised to the n, you're going to have n plus 1. On the bottom, instead of n factorial, you're going to have n plus 1 factorial. My a sub n is the same, but because of division, I reciprocal it. Then I have this term. Now I need to simplify this. I need to figure it out. I have n factorial here, n plus 1 factorial here. So I rewrite it as n plus 1 times n factorial. The reason I do that because I want to reduce the n here and the n here. Alright. From here, n plus 1 to the n plus 1 exponential n plus 1. You can write it as n plus 1 to the n times n plus 1 to the 1. That's the same thing because they have the same base. Think of exponential property, they have the same base. So you add the exponential, so it's going to be n plus 1. Again, I did that because I want to reduce these two terms. That's why I do that. So I reduce these two terms. So after that, I left with n plus 1 to the n, this one right here, over n to the n. So this is, the next step I did is both of them raised to the n power. So I can put them together as a fraction raised to the n. So from here to here is the same thing. Then from here, I rewrite it as n over n plus 1 over n because they have the same denominator, as you can see here. So n over n is just 1 plus 1 over n, everything raised to the n power. Now if you go back to 8.7, alright, go back to 8.7, limit as n go to infinity, 1 plus 1 over n to the n is equal to e. I believe I proved this in my lecture. It's in 8.7. So e is greater than 1. So as the theorem 9.17, we see that the second condition is diverges. Alright, let's look at the next example. Hi, let's go to our next example. We have alternative series here. As you can see, negative 1 to the n means it's alternative. You're going to have plus, minus, and so on. So I'm going to let my 2 to the n over n factorial be my a sub n. So a sub n plus 1, you just add the 1 to all the n. So instead of to the n power, it's going to be n plus 1. Instead of n factorial, it's going to be n plus 1. Then I put them in ratio. The a sub n plus 1, the one here is go on the bottom, right here. Plus 1. Alright. So the a n sub 1 is going to be on the numerator. A sub n is going to be on the denominator. So again, this is my a sub n plus 1. Instead of divide, I change it to multiplication by reciprocal, the second term. Now I need to simplify this. So I have n factorial here. I have n plus 1 factorial here. So I'm going to rewrite this as n plus 1 times n factorial. It's the same thing. That way I can reduce the n factorial and the n factorial. Now I have 2 to the n plus 1 and 2 to the n. I'm going to rewrite the numerator as 2 to the n times 2 to the first. It's the same thing because it's the same base. If it's the same base, you just add the exponential. For the reason that I can reduce 2 to the n and 2 to the n. After I reduce these 2 and these 2, I left with 2 over n plus 1 as n limit as n go to infinity. This is equal to 0. So 0 is less than 1 by the ratio test. The series is converges. Alright. So let's look at the last example for ratio test. Again, I have an alternative series here. As you can see, I have minus 1 to the n minus 1. Now, a sub n will be 3 over 2 to the n over n squared. Again, a sub n plus 1, you just add 1 to all your n on the exponential and on the n here. You put them in ratio. So this is my a sub n plus 1 divide by, but I change it to multiplication, so reciprocal the second term. Now we're going to have to find a way to simplify this. I have 3 over 2 to the n plus 1 and 3 over 2 to the n. So I'm going to rewrite the numerator. The numerator will be 3 over 2 to the n times 3 over 2 to the 1 to the first. It's the same thing as this. 3 over 2 n plus 1. For that reason, I can reduce this and this. I'm thinking this is not factorial, so I can rewrite this. So that's all I can simplify for now. So I rewrite this 3 over 2 times n squared on the denominator. What I did on the denominator here, I expand this. This is n plus 1 quantity squared. If I expand this, I'm going to have n squared plus 2n plus 1. So this is what I have from expand n plus 1 quantity square. Now I have 3 over 2. So the 2 basically multiply to every term on the denominator, and the 3n squared, that's what we have left on the numerator. From here, I divide every single term by n squared. Alright, I divide the numerator and every term on the denominator by n squared. So I'm going to have 3n squared over n. I distribute the 2 in each term. So I have 2n squared, but I divide every term by n squared. So I have 2n squared over n squared plus 2 times 2 is 4n over n squared. 2 times 1 here is 2 over n squared. And then simplify the n squared. This n squared cancel. I left with 3. This n squared cancel. I left with 2. I have 4n over n squared. So I have 4 over n left. And the last term, nothing I can do, just 2 over n squared. Now if I take a limit, as you can see, I need to mention this. I dropped the absolute value because I know it's going to be positive. Alright, I know it's going to be positive. Now as n go to infinity, this term will go to 0 and this term will go to 0. So I end up with 3 over 2, which is greater than 1, and by the ratio test, this is the divergence. Alright, let's look at the root test next. Alright, the next one is called the root test. This is theorem 9.18. The theorem said that if you have a series a sub n, and if you put them in absolute value and take nth root, and you get less than 1, you can conclude that it converges absolutely. If you take it into absolute value and take into nth root, and you get something greater than 1 or infinity, you can conclude that the series is diverges. Now, if you have 1, you can say that it's inconclusive. Let's look at our example here. I have sigma n from 1 to infinity, 2 to the n plus 1 quantity to the n factor into n power, exponential n. So this is my a sub n right here. Alright, my a sub n is 2n, n plus 1. So what I'm going to do, I'm going to put in the absolute value, and I'm going to take root, nth root. That's what I did here. Put in the absolute value. I have to put in the absolute value. I did not. But it's going to be positive. So let's put in the absolute value here. Alright, and take the nth root. Alright, so from here, you're going to have 2n over n plus 1. The next step is I divide every term by n, the numerator, and every term on the denominator. So the n cancel out, I left with 2 on the numerator, denominator, n over n is just 1, and plus 1 over n. Now I take a limit as n go to infinity, this term will be 0, so I end up with 2. 2 is greater than 1, so by the root test is diverges. Alright, so let's look at the next example. I have the series here. Again, what I did is I put in the absolute value and take nth root. So from here I get n minus 2 over 5n plus 1. Next step I did is I divide every term by n. So n over n is just 1. Minus 2 over n, I can't do anything, so it's just 2 over n. The denominator, the n cancel, I left with 5 plus 1 over n. Next step I did, I take the limit as n go to infinity. So 2 over n go to 0, 1 over n go to 0. I have 1/5. Absolute value of 1/5 is 1/5, which is less than 1, so it's converges. Alright, let's see the next example. Hi, let's look at our last example for the root test. I have this sequence here, alright, 2 to the nth root of n plus 1, the whole thing raised to the n power. So this is my a sub n right here, my a sub n. So I put it in absolute value and nth root. And then I end up with this term right here. My big question is, if you take a limit as n go to infinity of 2, it's just 2. You take a limit as n go to infinity of 1, it's just 1. But if you take a limit of n go to infinity, square root of n, nth root of n, we don't know what it is. Alright, so what I'm gonna do is I'm have to figure out what is this equal to. So I let it equal to y. Right, I let it equal to y. The next step, I take out n both sides. So I take out n on the left and I take out n on the right. So I have ln y equal limit n to infinity, ln nth root of n. Alright, next step, I rewrite radical as exponential. Nth root is the same thing as 1 over n. Next step, I use the property of exponential. I can bring the exponential up front. So it's going to be 1 over n ln n, limit as n go to infinity. The next step, I'm just rewrite it. 1 over n ln n is the same thing as ln over n. Now if you take a limit as n go to infinity, you're gonna have infinity over infinity. So I'm gonna use L'Hopital's rule here. When you have infinity over infinity or 0 over 0, you can use L'Hopital's rule. So I'm gonna take derivative of numerator. Derivative of ln is 1 over n. Take derivative of n, it's just 1. Now I'm gonna as n go to infinity, my numerator will go to 0. Alright, my numerator will go to 0. So 0 over 1 is just 0. So we get this whole thing equal to 0. So we start from ln y. Ln y equal to 0. Ln is log base e. So instead of write ln y equal to 0, I can rewrite it as y equal to e to the 0. Anything to the 0, e is just 2 point something. Anything to the 0 is just 1. So my y is equal to 1. This is my y right here. We did it right here. So my y is equal to 1. So limit as n go to infinity, nth root of n equal to 1. So I was be able to solve for the unknown here. So limit of this whole thing, limit of 2 is just 2. Limit of nth root of n, I just solve it, which is 1 plus 1. 2 plus 1 is 3. 3 is greater than 1. So by the root test, the series is divergent. Alright, we finished 9.6. Bye.